Welcome to qnawire.
For this problem, we want to consider 6 particles arranged in a regular hexagon of side length A, where each will move with a constant speed v towards its nearest neighbor. So at time t0, our hexagon looks like this. Eventually, all of these particles are going to meet each other, and we want to figure out how long does that take. Sometime after they've started moving, we'll call it T1, our hexagon is going to look a little bit different. Each particle will have moved some amount, and we need to connect them together to define our new hexagon so that we know what direction each particle is moving in. So now if we consider this particle, it's moving in this direction along the red lines. They're going to keep moving, and sometime later, let's call it T2, they're going to have moved some distance in the direction of the red lines, and we can connect our green dots together, particles together, to create our new hexagon. And the particles will be moving along the green lines. At a future time T3, they're going to be moving again. We can draw where our particles might be then, connect them together to create the new hexagon. And now they're going to be moving along the blue lines. And the hexagons are going to get smaller and smaller and smaller until all of them meet in the center of the hexagon. So, in order to figure out how long that takes, we are going to leverage the fact that speed is equal to distance over time. And so, doing a little bit of algebra, we know that time is going to be equal to distance divided by speed. But we can't just use the distance that it travels and the constant speed v. Because it's changing direction, we need to pay attention to that. So let's redraw our initial hexagon. And I'm just going to consider this particle in this upper right-hand corner. In order to get to the center of the hexagon, it's going to have to travel this length r. And because this is a rectangular hexagon, we know that the length r between any corner and the center is going to be equal to the length of one side. So this is going to be equal to the length of the side A. We also want to consider this angle theta here between the speed v of the particle and the length or distance that it travels A. And again, for a rectangular hexagon, the total angle of each of the angles in the hexagon is 120 degrees. So half of it, which is what's drawn here, is going to be equal to 60 degrees. That means that if we want to find the component of the velocity that is along the line A, so I'm going to draw that in with red. So we want to find this. That is going to be equal to V cosine theta. So now we know the distance that it travels is A, and its speed in that direction is V cosine theta. Or this V cosine theta can also be thought of as the rate of decrease of A. Cosine of 60 degrees is equal to 1/2, and so this is going to be equivalent to 1/2 V. When we go back to our equation and plug in, now we know that time is going to be equal to the distance, which we now know is A, divided by the speed in that direction, which is 1/2 V. And we can make this look a little bit nicer by doing a little algebra and writing the 1/2, dividing by 1/2 is the same as multiplying by 2. So this is the same as 2a over v. So it will take a time equal to 2a over v for all of the particles to make it to the middle and meet with each other.